Okay, so now let's go over question 9, sorted eggs and hash browns. Part A is called IOs and dollars. So your company is switching compute plans and they need your help to figure out the most cost-efficient way to process your data. Each buffer page costs $10, but the cost of each IO is variable. You're given a choice between three plans. And so these are the three plans here. The difference between the plans is in the number of buffer pages and then also in the cost per IO. So in plan 1, you have 100 buffer pages, but a cheaper IO cost at 1 cent per IO. Plan 2, you have 50 buffer pages, but a more expensive IO cost at 5 cents per IO. And then plan 3, you have only 10 buffer pages and a more expensive IO cost at 25 cents per IO. So your company decides to go with the trial plan first and gives a small table to sort to see how it goes. With a file size of 100 pages, how many IOs are incurred in sorting the file under each of the plans? So let's first go over how we calculate sorting, just a quick reminder. So the way that we calculate sorting is that first there is a conquer pass in the sorting algorithm where it divides the pages into a number of runs that are the size where each run is size B pages, where B is the number of buffer pages. And then once it divides those runs, it merges the runs in the conquer phase, in the next phase, where it starts merging together runs to ultimately get one sorted run. So in this phase, when it's merging together the runs, it can take multiple passes. So the ultimate IO cost is going to be however many passes it takes plus 1 for the conquer phase pass, and then we'll multiply that by 2n, where n is the number of pages, in this case 100. The reason for that is because in each pass, you're doing a read of all the pages and then a write of all the pages. So that's why it's 2. 1 for the read, 1 for the write. So we just need to figure out the number of passes and then multiply that by 2n to get the total IO cost. And we can always verify this number of passes by doing log base b minus 1 of n divided by b. Because n divided by b is the number of runs that we have, and then b minus 1 is the amount of runs that we're able to merge at the same time. So in part I, we're asked to figure out how many IOs are incurred under plan 1. So in this case, in plan 1, what will happen is we'll read in the 100 pages, and then that will just get sorted in memory because we have b equals 100. So this sort happens in memory. This is the conquer phase. So this sort happens in memory, and because of that, we have it completely sorted after that in-memory sort, and then we just have another 100 to write. So the total IO cost here is just 200 IOs. We read in all 100 pages, sort that in memory because we have b equals 100 buffer pages, and then we just write them back down. So if we were to put this in terms of our formula, we had one pass, and then we multiply that by 2n, which is equal to 200. Then we're asked how many IOs are incurred under plan 2. So in this case, we read in the 100 pages. We sort this in memory, and so what's going to happen is, in this case, we only have 50 buffer pages, so we're going to get 2 runs of 50 pages. Right, and each of these runs is sorted. Then we need to merge those runs together. But first we write the runs to memory, right? So that's going to be 100 to write the runs, to disk. So we write the runs to disk. It's going to be 100 IOs to write it to disk. Then we read it back in, and we read those runs back in, and then we merge the runs together. In this case, that's just going to take one pass because there's only 2 runs, and we can actually merge up to 49 runs because we have 50 buffer pages. So we merge the runs, and then we write that fully sorted run of 100 pages. So in this case, there are 400 IOs. And if we, again, put that in terms of our formula, we had 2 passes, the conquer phase and then the merge phase. So multiplying that by 200 yields us 400. Now we're asked how many IOs are incurred under Plan 3. So first we read in the 100 pages. In this case, we have 10 buffer pages, so we're going to end up with 10 runs of 10 pages. We write those pages to disk. Then we read those pages back in from disk. So in this case, we have 10 runs, but we can only merge together 9 runs at a time. So in this case, we're going to merge the runs, but we're only able to merge together 9 runs at a time. So 9 of the runs get merged, and then we have a leftover run. So we're going to merge the runs, but now we have 2 runs. So we're going to write those 2 runs back to disk. We'll read the 2 runs back in. We'll merge the 2 runs, which in this case is fine because we can merge 9 runs at a time. So we merge them into one final run and then write that back to disk. This is 600 IOs. And so if we were to put that in terms of our formula, we had 3 passes, the conquer pass, and then 2 merge passes, and that was, when you multiply by 200, 600 IOs. So then we're asked which plan is cheapest for this scenario. So first, let's take into account the fact that each buffer page costs $10. So we have Plan 1, Plan 2, and Plan 3. So off the bat, each buffer page costs $10. So Plan 1 is going to cost $10 for each of the 100 buffer pages, which is $1,000. So 1,000. And then Plan 2 only has 50 buffer pages, so that's going to cost 500. Plan 3 only has 10 buffer pages, so that's only going to cost 100. And then we're going to add the cost of actually sorting, or the cost of the IOs that come from sorting. So for Plan 1, there were 200 IOs, and each of these costs 1 cent. For Plan 2, we had 400 IOs, and each of these costs 5 cents. And then for Plan 3, we had 600 IOs, and each of these costs 25 cents. So for our total cost, we're going to have $1,002 for the first plan, $520 for the second plan, and then $250 for the third plan. So in this case, Plan 3 is the cheapest. So your company is happy with the results and now wants to sort a file of size 10,000 pages. And then we're asked to basically do the same thing, just with a higher N in this case. So under Plan 1, we read in the 10,000 pages. That gets divided right into 100 runs of 100 pages because we have 100 buffer pages. And then we can only merge together 99 runs at a time. So first we write those runs back to memory, or back to disk, and then we read them back in. And so right here we have 100 runs, but we can only merge 99 of them at a time. So we end up with 2 runs here because we merge 99 of them together and then we have 1 run left over. So we have 2 runs. We write that back to to disk. Keep saying memory, I mean disk. We write that back to disk. We read that back in. We merge the 2 runs, so now we only have 1 run, and then we write that back to disk. And so in this case, if we add all that up, we have 60,000 IOs. And if we put that in terms of the formula, we had 3 passes because we had the 1 conquer pass and then 2 merge passes. And you multiply that by 2 times the number of pages, in this case n, which is, in this case, 10,000. So 3 times 20,000 is equal to 60,000. Then we're asked how many IOs are incurred under Plan 2. So again, we read in the 10,000 pages. We get 200 runs of 50 pages. We write that to disk. We read from disk. So now we can only merge 49 pages at a time. or 49 runs at a time. So we have 200 runs. We merge 49 of them. We merge another 49 of them. We merge another 49 of them. We merge another 49 of them, and then the remaining 4 get merged together as well. So now we have 5 runs, right? So now we have 5 runs, and we write those to disk. Then we read them back in. We merge all the runs together, so now we only have 1 run, and then we write that to disk. And this is also 60,000 IOs. So again, if we think about this in terms of the formula, there were 3 passes, right? We had the one merge phase, or the one conquer pass, and then we had 2 merge passes. There were 3 passes, and then again multiplied by 20,000 is equal to 60,000. Now we're asked how many IOs are incurred under plan 3. So in this case, we have the 10,000 pages, and then this gets split into 1,000 runs of 10 pages. So again, all of these runs are sorted, right? But we only have 10 pages sorted at a time. So this is a lot of runs. So we write all those runs to disk, 10,000 IOs. We read them back in. So we have 1,000 runs, but we can only merge together 9 runs at a time. So this is going to create a ton of runs, right? Like even because we can only merge so few at a time. So this will create 112 runs. So we have 112 runs. We write that to disk, and then we read that back from disk. Again, we can only merge 9 runs at a time. So we merge 9 runs at a time, which gives us, so I'm just going to continue over here, 13 runs. And then we write that back, and then we read it back. So we have 13 runs that we need to merge together. This, again, we can only merge 9 runs at a time, so we're going to end up with 2 runs now. And then we're going to write those to to disk, and then we're going to read them back in. And then now we can just merge that into 1 run, and then write that back to disk. So the IO cost here is much heavier. And if we add this up, we have 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, 100,000 IOs. And then if we were to put that in terms of our formula, which is probably a lot simpler, we have 5 passes. And each of those was 20,000 IOs, which yields us 100,000 IOs. So if we were to use that log formula to verify this, so we have the 1 right from the conquer phase, but then to get the other 4 passes that we went through in the merge phase without going through it like I did, we could have just used a log. So in this case, a log of b minus 1, log base 9, because that's how many runs we can merge together at the same time. And then we do n divided by b, in this case 10,000 divided by 10, which yields 1,000 to get the number of runs, right? Because in this case there are 1,000 runs of 10 pages. So we say we have 1,000 runs, and then we're using log to indicate like we're merging 9 runs at a time. And then that will give us how many passes it takes to actually merge 9 runs. Like if you merge 9 runs at a time to eventually condense down to 1 run. And so in this case, this would yield you 1 plus 4, which is 5. So that's another way to get that it's 5 passes. So you could either use the formula, or you could do it as I did it, and just sort of think your way through it. So now we're asked which plan is cheapest for the n equals 10,000 pages scenario. So the first thing we can do is just copy the beginning part of this analysis, because the overhead of the buffer pages is not changing at all, right? It's still the same number of buffer pages, and those are still the exact same cost. The only thing that changed from part from part A to part B was the number of IOs. So for this, we see that part I of part B had 60,000 IOs, and those each cost 1 cent. Then plan 2 also had 60,000 IOs, but these cost 5 cents. And then plan 3 had 100,000 IOs, and these each cost 25 cents. So you could see the difference between part A and part B was that in part A, the cost of the buffer pages kind of dominated the overall cost of each plan. However, in part B, we see that the cost of the IOs is dominating the cost of the plan. And in this case, because the file was bigger, we had much more IOs. So that's the reason why. And so because of that, when we calculate the cost for each of these, we'll see that plan 1 is vastly superior because its IO cost is much smaller. So for plan 1, the cost was $1,600. For plan 2, the cost was $3,500. And then for plan 3, the cost was $42,600, I believe. So we can see that pretty handily plan 1 is the cheapest in this case. So now let's go to part C, which deals in hashing. So the company inquires about hashing a smaller table where n is equal to 100, assume uniform hashing with a perfect hash function. We're asked how many IOs would it take to hash this table under plan 1. So remember, the way that hashing differs from sorting is that with hashing, you don't necessarily write the same number of pages that you read in because of how you're hashing the pages evenly across buckets. And you might have an odd number of buckets that doesn't evenly divide the number of pages. So we round up to indicate the number of pages in each bucket because we don't deal in fractional IOs, right? There's no such thing as a fraction of an IO. And so because of that, you may have more IOs when writing than when reading. So it's not as simple of an analysis, and you're actually going to have to think through each pass. So you can't just do that simple log formula that we had with sorting. So in this case, with plan 1, we can read in the 100 pages, and then we can hash it into 100 buckets. And then we just write that back to disk. So in this case, it would only take one pass, right? So 200 IOs. Then we're asked how many IOs it takes under plan 2. So for plan 2, what happens is we read in the 100 pages. And so again, remember there's 2 phases. So in this case, we were able to skip the first phase in part I and directly skip to the second phase. But the phases are, the first phase is the partitioning phase. So we get each of the partitions to be small enough to fit within memory. And then in phase 2, we build an in-memory hash table. In part I, right, of part C, we directly skipped that second phase. Our partition in this case was just one partition of size 100. And so we could just directly read in that partition because it's B pages large. So we read in the 100 pages directly, and we built the hash table in memory. However, for plan 2, our partition is too big. We only have 50 pages, so 50 buffer pages, so that one partition of size 100 pages is not going to fit into memory. So we're going to have to partition it. So we take the 100 pages, and we hash it into 49 buckets. So in this case, when you do 100 divided by 49, that is going to give you 2 point something, which we round up to 3. So we get 3 pages in 49 partitions. And so that's going to be a write cost of 3 times 49. Then we read back in that 3 times 49 because now we have 3 partitions of size 49 pages, we have 49 partitions of size 3 each. Since 3 is smaller than 50, we can take each partition and build an in-memory hash table of it. So we read in all those pages again, we build the table. Right, so this is the build table phase, and then we write those tables back. So we're building multiple tables, right? A table for each partition, and we write those tables back to disk. In this case, that ends up being total 541 IOs. So we're adding 100 plus 3 times 49, which is 147, plus 147 plus 147 to get 351, or 551, sorry. Then we're asked how many IOs does it take under plan 3. So we read in 100 pages. These get split across 9 buffer pages to give us 11 point something, rounded up to 12 pages per partition. So we have 9 partitions of 12 pages each. Then we write those to memory. So let me just be consistent here. We have partitions of size 12 pages, and we have 9 partitions. Then we read those partitions back into memory. And in this case, because the partitions are too big, right, since they're size 12 pages and we need them to be 10 pages or less because our memory is 10 pages, we're going to have to do more partitioning. So we read in 12 times 9 pages, which in this case is going to be 108 pages. So we have 108 pages, or think about it as each partition being 12 pages. We need to divide those 12 pages into partitions. So the 12 pages, right, will get divided by 9, and that gives us 1 point something, which rounds to 2 pages per partition, or 18 pages total per partition. So 2 pages per the small partitions, right, but then 18 pages per the larger original partitions. And so in this case, we are going to write 18 partitions, 9 partitions of size 2, or 18 partitions for each of the 9 partitions. So this gives us 18 times 9 IOs. And then at this point, they are small enough, since they're size 2, to fit into memory. So we're going to read that back in, build the tables, and then write them back out to disk. And so that is going to yield us 802 IOs. So to really quickly recap that last part, because I know the numbers get kind of confusing, what happens is we have 9 partitions of 12 pages each. 12 is bigger than 10, so we need to partition each partition into more partitions. We have 9 partitions. Each of them is 12 pages large, so we need to partition each of those 12 pages. Those 12 pages get partitioned across 9 buckets, because again, we have 10 buffer pages, we can only use 9 of them to do the partitioning, because 1 buffer page is the output page. So we take the 12 pages and partition those across 9 pages. So we round up to say there's 2 pages on each of those 9 pages, in each of those 9 buckets. So total 18 pages. So each partition of 12 pages gets converted to 9 partitions of 2 pages. So each partition that used to be 12 pages is now 18 pages, because it's 9 partitions of size 2 pages. So that's why we go from 12 times 9 to 18 times 9. But really what that 18 times 9 represents is that those original 9 partitions got split into 9 partitions themselves. So now you have 81 partitions, and those are each size 2. And so ultimately, we have 81 partitions that are each size 2 pages, and then we build the hash tables from that. So we end up having 81 hash tables. So now let's calculate the cheapest plan. So here we can just paste the previous analysis, because again, the only thing that's changing is the IO cost, but not the actual cost of the buffer pages themselves. So now let's just plug this in. So we have 200 IOs for plan 1. Each of these are 1 cent. Then we have 541 IOs for plan 2. Each of these are 5 cents. Then we have 802 IOs for plan 3, and each of these are 25 cents. In this case, plan 1 costs $1,002. Plan 2 costs $522.55. Whoops. And then plan 3 costs $300.50. So plan 3 is going to be the cheapest plan. And notice that in this problem, like the first part A, it's actually the cost of the buffer pages, which ends up sort of dominating the final monetary cost here. And that's also because we used a smaller table, right, where n was equal to 100. So now let's look at part D, which is a true or false section. So mark all statements that are true. The first statement is hashing will always result in the same number of IOs writing to disk as the IOs reading from disk. We just went over this. This is not true. right? If the number of partitions is like an uneven number that doesn't evenly divide n, then we're going to end up having to round the number of IOs per partition because there's no such thing as a partial page, right, or a partial IO. And so you can actually have more IOs writing to disk than IOs reading for disk in hashing. In sorting, however, that is not true. It's always the same number of IOs writing to disk as IOs reading from disk because we're not doing that like partitioning across pages or across buffer pages. So then in the third statement, we're told you can only build an in-memory hash table if you have b minus 1 pages as your partition file size, where b is the number of pages in the buffer. So this is incorrect, right? It's when you have b pages, b or less pages as your partition file size. And that's because we have b total pages that we could build the hash table out of. So just load all those pages into memory and then build the hash table out of the b pages. You don't actually need to like reserve an extra page or anything. That would make it so that you only have b minus 1 pages. This would actually work with a partition file size of b pages. So this is also false. And then the last statement is, assuming uniform data spread and no key skew with b pages of memory and a file size of n pages, hashing a table will always be at least as costly as sorting it. So in this case, right, with hashing a table, the two scenarios are the write IO cost is the same as the read IO cost, or it's higher. But in the case where it's the same as the read IO cost, well, that's just the exact same as sorting, right? It's the same cost as sorting. You end up having the same number of passes, and each pass will cost you 2 n IOs because you have n IOs for reading and n IOs for writing. Now, it's possible that it could be more, right? Because you could have n IOs for reading and then something more than n for writing in the case of hashing. But it is true that hashing a table will always be at least as costly as sorting it. At least is the key word here. So this is true. It would be incorrect if you said that it's the same as sorting. And it would also be incorrect if you said that it's always more than sorting, because it's not necessarily true that the write cost will be more than the read cost. So in this case, this is true as well. So part B and part D are both true, and that wraps up this question.